To begin this lesson, let's define something called sigma notation. Here is the capital letter, the Greek letter sigma, and in math terms, this is often used when you want to describe a sum, when you're adding things together. Let's describe how it works by looking at this example. The sigma means we're going to add things of the form 5i plus 2. This I equals 1 down here tells you where to start, and this 3 up here tells you where to stop. So I'll take this expression, I'll put 1 in place of I, I'll then put 2 in place of I, and then 3 in place of I. And I'll add all those things together. It'll look like this. 5 times 1 plus 2. We then move on to 2. 5 times 2 plus 2. Then we move on to 3. 5 times 3 plus 2. And I'm adding these things together. After entering this into a calculator, I see that the value is 36. So we'll use this notation later in the lesson, along with these three formulas. These are not to be memorized, but we will use them later on. I would like to go over an example describing how they work. So let's start with this one here. This says you add the number 1, starting at 1 and going to some number n. Here, this n just means any number. It could be 5, 100, 5,000. In example 1, part A, let's let n equal 500. I want to add the number 1 to itself 500 times. Notice that there is no I in this expression, so at each step, you're just going to copy down the number 1. You'll start with I is equal to 1, but for that part of the sum, you just put 1. You then move on to 2. Again, you just put a 1. Move on to 3 and put down 1. And you keep going until you do this 500 times. So this is 500 times. And what should this sum equal? Probably no surprise that it's equal to 500. In fact, the answer will be whatever number is up here. And that's exactly what this formula says. If you start at 1 and you're just adding the number 1, you'll get n, the value that you put at the top. Let's also look at the second formula. This says what happens if you add I going from 1 to n. So here I chose n is equal to 300. This is what the sum would look like. You start I is equal to 1, so you're just going to put down a 1. Then you go to I is equal to 2, so you put down a 2, then a 3, then a 4, then a 5, and you would not stop until you get to 300. Now, if you tried to do this in a calculator, it would take a very long time. But that's where this formula will come into play. Instead of actually doing the sum, what we can do is say, well, n is equal to 300. If I want to evaluate the sum, we can just put 300 in place of n in this expression. So by the formula, this sum is equal to 300 times 300 plus 1, all divided by 2, which is 300 times 301, all divided by 2. This is a quick computation. This sum is equal to 45,150. Now, again, it'd be very long to perform this sum, but since we have this formula, we can get the answer quick. And the same thing can be said if you had a squared here and perform this sum. If you want to know the value of that thing, you wouldn't actually do the sum itself. You would just put n into this formula to get your answer. So on the previous slide, we looked at this sum, and just to write it out again, we said this was equal to 5 times 1 plus 2, then add on to that 5 times 2 plus 2, and then finally add on to that 5 times 3 plus 2. And we said the answer was 36. Great. Since this is all being added together, the way in which you add it really does not matter. You could have put all of the terms with the 5 first and all the 2's last. So your sum could have looked something like this. You could have said, oh, well, this is equal to 5 times 1 plus 5 times 2 plus 5 times 3, then plus 2 plus 2 plus 2. The order in which you add these does not matter. Also, since there's a 5 common to these three terms, you could factor it out, and you could go on to say, oh, well, this is also equal to 5 times 1 plus 2 plus 3, then plus 2 plus 2 plus 2. When it comes to adding terms together, if there's a common number, it can be factored out. And also, the order in which you add things really makes no difference. I bring this up because there are these two formulas here that look very abstract, but they try to describe these ideas. Like this one here. This one says if c is a constant being multiplied to something in a sum, you can factor that thing out from the sum. So maybe just as a short example, if you said if we sum I goes from 1 to n of 5i, well, I know how to do this. This is 5 times 1 plus 5 times 2 plus 5 times 3. But as we just saw, you can take that 5 out from every single term, which is 5 times 1 plus 2 plus 3. And here, this is the sum of not 5i, but the sum of just I, which is 5 times the sum of I going from 1 to 3. This means that if you have a constant inside a sum, like 5, you can skip to this last step and say just factor it out. Also, if you're adding or subtracting two parts in a sum, you can split that sum into two pieces. Let's actually use this in this example here. So looking at the example at the top again, we're looking at the sum of I going from 1 to 3 of 5i plus 2. According to this rule, whether you add or subtract, you can split it up into two separate sums. It does not matter the order in which you add these things together. You could say this is equal to the sum of I going from 1 to 3 of 5 times I plus the sum of just 2. Here, this property says, oh, well, this 5, you can factor it out. In fact, you can factor the 2 out of this sum and just put a 1 here. So this becomes 5 times the sum of I going from 1 to 3 of I plus 2 times the sum of I going from 1 to 3 of just 1. Now we have formulas for all this stuff. We have a formula for adding I as well as for adding 1. For the first one, that's going to be 5. Okay, here n is equal to 3, so the sum's going to be 3 times 3 plus 1 over 2. We'll add on to that. Well, if you sum just 1 going from 1 to 3, I know the answer is going to be the number at the top, which is just 3. So this is 2 times 3. Okay, what does this simplify to? It should be 36. Okay, this is 4 times 3, which is 12, over 2 is 6. And 6 times 5 is 30. Plus 6 is 36. The point of these two rules is it can simplify a sum for you. If you have a sum within the sum, you can break it apart. If you have numbers, like a 5 or a 2 within the sum, you can factor those out. Let's move on to the main topic of this section, and that topic is the definite integral. Here I have its definition, and I'll state it. The definite integral is the area bounded by a given function and the x-axis between two given x values, a and b. To make sense of this definition, let's look at a specific example. Here I have a function f of x is equal to x. I want to find the definite integral of this function on the interval from 0 to 3, that is a starting at 0 and b ending at 3. I'm first going to draw that in here. So here is the function f of x is equal to x. Here is the starting point, and here's the ending point, and I want the area that's bounded by the x-axis and the function from here to here. This is the area. It is bounded by the function and the x-axis. It's this. The definite integral is the area of that region, and it's a triangle. If you want to find the exact area, that is 1/2 the base times the height. So what is the base of this triangle? The base is 3. What is the height of the triangle? Well, since the function is f of x is equal to x, the height is also 3. And so the area is 1/2 of 9, or 9/2, or really, if you'd like as a decimal, 4.5. So this is the definite integral of this function on the interval from 0 to 3. Again, it's a number, and that number represents an area, the area bounded by the function itself and the x-axis. We will use a very specific notation when talking about the definite integral. In general, we'll write it like this. This symbol is a stretched letter S. Where the area starts, we'll call the lower bound, and we put that number here, so I'll put this is A. Where the area stops is the upper bound, and I'll call that B. Next to the stretched S, we put the function, so in general, that would be f of x, and we multiply it by dx. This symbol represents an area, and that area, again, is bounded by a function and the x-axis between these two x values. So what's 4.5? Using this notation, that's the definite integral from 0 to 3 of the function x dx. We were able to solve this because we ended up with a figure, a shape, whose formula we know the area for. What happens if we change the function slightly? What if it wasn't x? What if it was x squared, for example? Let's talk about that in the next example. In example 3, let's write the definite integral for the function f of x is equal to x squared on the interval from 0 to 2. And as a guide, here we have the function f of x is equal to x squared. So the definite integral is written like this, from 0 to 2, where we start and end, of the function x squared dx. And what this represents is the area between this function and the x-axis starting at 0 and ending at 2. So it's going to be this region here. So this area. What does that equal exactly? And the issue is, well, I don't really know because there's a curve to this equation. So we can't simply just use the formula for the area of a triangle, let's say. When this happens, what we'll do is we'll estimate it. So we can't find it exactly, but we'll approximate it. We're going to do this by using r sub 2. I'll describe the procedure for computing this thing and talk about why it's called r sub 2. So here's the process. You take the interval from 0 to 2, and you divide it into a certain number of pieces of your choosing. And here I'm going to divide it into 2 equal pieces. So let's write that down. I'm going to divide the interval from 0 to 2 into, I'll say n is equal to 2 equal pieces or parts. It works nicely for this interval because the length of the interval is 2, and if you split it into 2 equal pieces, the first one goes from 0 to 1, and the second goes from 1 to 2. We're going to use these as the base of a rectangle. So in this first part, from 0 to 1, I'm going to construct a rectangle using this function. And I'm going to do that by choosing the right endpoint, which is at the number 1. I'm going to take that number, put it into the function to get the height of the rectangle. So let me draw that in here. It would look like this. And actually, this is a square. What is the area of that square? Well, it's base times height. The base is 1, and the height is determined by taking the right endpoint and putting it into the function, so squaring 1, which actually is also 1. So no surprise here. This is the formula for the area of this square, and it simplifies to 1. We now repeat this for the second piece. So to this, we're going to add on the area of the rectangle whose base is 1 and whose height is determined by the right endpoint. So 2 squared is equal to 4. If we write that out, the base has length 1, the height has length 2 squared, which is 4, and I'll draw that in here like this. So here we have an estimate of the area of the definite integral. If we simplify this thing, so that's going to be 1 plus 4, and that is 5. So this number 5 is our estimate. In fact, if you look at it, it's a lot more than we actually needed. So we could be more specific and say that this is an overestimate. And that's determined just by looking at the graph itself. This is too much. So the procedure that I've outlined here, this thing is what we call r sub 2. The 2 means we're using 2 rectangles. And the capital R means we're using right endpoints. So in general, if you want to estimate the definite integral using r sub n is n rectangles using right endpoints. So let's expand on this. Let's see if we can get different estimates and, in fact, maybe get better estimates for the exact value of this definite integral. So in example 4, what we'll do is use the same function f of x is equal to x squared, and we're going to come up with 3 different estimates. We will estimate the exact area by using L2, M2, and R4. Let's start with estimating the definite integral by using L2, and I'll draw that in this picture here. So for this one, this is going to be L sub 2. If we want to approximate the integral from 0 to 2 of the function x squared dx, L2 means, the 2 being, we divide the interval from 0 to 2 into 2 equal pieces, but instead of using the right endpoints, this capital L means use the left endpoints instead. So the process would look like this. We have the interval from 0 to 2, and we're going to divide it into 2 equal pieces. And like last time, that just means you have 0, 1, and 2 as endpoints. I'm going to first draw in L sub 2. On this first interval, the length of the base is 1, so I'll first write that. That's the base of the rectangle. And then here I'm going to put the height. The height is determined by using not the right endpoint, but the left endpoint. Well, the left endpoint is at x is equal to 0. The function's x squared. If you square 0, you get 0. In fact, this first part contributes no area, and that can happen, and that's because this is just an estimate. To complete this, we'll now do this for this next piece. Okay, so here's the base, but to get the height of the rectangle, I'm going to use the left endpoint, which is 1. And if I draw this in here, I get this. That would be the base is 1, and the height is 1 squared. And when you add this all together, that's 0 plus 1, and 0 plus 1 is 1. And this is the value of L sub 2. This is an estimate. In fact, this is an underestimate. You can see that, like we're missing some of the area. All right, well, I have an idea for what L and R mean. It means either use the left or the right endpoints of your intervals. What would M sub 2 mean? And I'll put that one here. So like, what is M sub 2? So the 2 still means we're dividing the interval into 2 equal pieces. But now the M means if you want the height of your rectangle, you're going to use the middle of the intervals. So let's compute that one next. If we want to compute M sub 2, I'll first draw in the rectangle. The base is 1, and the height is coming from, well, this must be at a half, 1/2 squared. So I'll draw this in here. So here's the height. The base has length 1, and this is happening at a half. And we get this area here. So to start M sub 2, the base is 1, and the height is 1/2 squared. So we get 1 times 1/2. You could just use 0.5 squared. To that, we're going to add, all right, so here the middle is going to be at 1.5, or if you'd like, you can use a fraction and say, well, that's at 3/2. That'll give me the height of the rectangle. The base is still 1, but now the height is going to be 3/2 squared. So the base is 1, the height is 3/2 squared. And this is some number, which I'm going to type this into my calculator to get a value for it. So that's 1/4 plus 9/4. And that is 2.5. So this is the value of M sub 2. Now, is this an over or under estimate? It's not as easy to tell this time because for each rectangle that we have, sometimes the area is over, but sometimes it's under. So it's not as obvious in this case what's going on. Okay, so L2 means divide the interval into 2 equal parts, but use the left endpoints to get the height of the rectangle. M sub 2 means we're still dividing the interval into 2 equal parts, but we're using the midpoint of each interval. Let's do one more, R sub 4, and I'll put that here. So what does R sub 4 mean? We've discussed the L, M, and the R, but what does the 4 tell us? The 4 means you're going to use 4 rectangles instead of 2, and we've only used 2 up to this point. What does that mean about the number of rectangles and where they're located between 0 and 2? Well, if the length of the interval is 2 and you're dividing it into 4 equal parts, that means each rectangle has a base length of 1/2. How do I know this? You can think of it as a formula. Let's call delta x the length of the base of each rectangle. It's very easy to compute that. You can take the length of the interval, which is from 0 to 2, and you can divide it into 4 equal pieces. This is 2 over 4, or simply 1/2. So if we divide this interval into 4 equal parts, you're starting at 0, you then next go to 1/2, you would then go to 2 halves, which is 1, you would then go to 3 halves, or 1.5, and then you end at 2. So we're going to have 4 rectangles, and since we're talking about r, we're going to use the right endpoint of each interval. So let's actually write down what r sub 4 is equal to. We're now going to have 4 parts in our sum. So the first one, the length of the base is 1/2, and the height is going to be at 1/2 squared. So first I'll draw it in here, and I'll write it down here. That's 1/2 times 1/2 squared. To that, I'll add, okay, for this next one, the base is 1/2, but the height is at 1 squared, which is 1. So the area of that is 1/2 times 1 squared. And I'll draw it in like this. Okay, for the next one, the base is still 1/2, but now the height is at 3 halves squared. And there's one more. The base has length 1/2, and now the height is at 2 squared, which is 4. And I'm going to get a value for this in my calculator. Okay, as a decimal, I got 3.75, and that's the value of r sub 4. And again, this, I can tell from the picture, it's too much stuff. It's an overestimate. However, this is a better estimate than we got for R2. And the reason is, if you looked at R2, we were also including this stuff and this stuff, but now it's gone. And this brings us to a really important point. These are all estimates, but certainly they're getting better. And in fact, if you want to get a better and better estimate, you can increase the number of rectangles. You can always add more rectangles in here. We could have done 40 or 4,000 or 4 million. Every time you increase this value, sure, the computation is longer, but your answer is going to be more and more accurate of an estimate. In example 5, let's practice this idea just with a slightly different function. So here I have f of x is equal to 4 minus x squared. And I want to estimate the definite integral. That means I'd like to estimate this thing. So that was the function 4 minus x squared on the interval from 0 to 2. I want to estimate it using L sub 2 and R sub 4. Let's start with L sub 2. The interval is from 0 to 2. And if I want 2 rectangles, I'm going to divide this interval into 2 equal parts. So for L sub 2, since n is equal to 2, the length of the base of each rectangle is 2 minus 0 over 2, which is 1. And since we're using left endpoints, I'm going to use this first one and the second one when constructing the rectangles. So for the first rectangle, the base has length 1, and the height is going to be at 0 put into the function, which gives us this. So L sub 2 is first equal to, the base is 1, and the height is 4 minus 0 squared, or simply 4. To that, I'm going to add on this next one. The base is 1, and the height is going to be what we get if we put 1 into the function, like this. So it's going to be a base of 1, and the height is 4 minus 1 squared. If we simplify this, we get 4 plus 3 and our estimate is 7. I can see from the picture that this is an overestimate. So again, what's different here is how we're getting the height of the rectangle, and that's because the function's different. For this first rectangle, we're using the left endpoint, which you plug into the function. So the height means you take 0, put it into the function f of x, and in this case it's simplified to 4. Here, to get the height at 1, I put 1 into the function. Here, I simplified it down to 3. Let's repeat this for r sub 4. So over here we want r sub 4. Okay, so for r sub 4, we're using n is equal to 4 rectangles, and that means we're dividing the interval from 0 to 2 into 4 equal parts. So that's 2 over 4, and that is 1/2. So from here to here, that means we're starting at 0. I'll then go to 1/2, then to 1, then to 3/2, and then finally we'll end at 2. So for this computation, for r sub 4, the first rectangle is going to have a base of 1/2 and then a height of 1/2 plugged into the function. So this is 1/2 the base times the height, which is 4 minus 1/2 squared. Okay, to that, I'm going to add what we get at 1 using the right endpoint. So here, the base is 1/2, but the height is 4 minus 1 squared. Next, I'll add on, okay, I'm going to use the right endpoint of 3/2 plugged into the function. And this is going to be a base of 1/2 times the height of 1 minus 3/2 squared. And then finally, I'm going to use, again, the right endpoint, but the right endpoint takes me to 0. So this is going to be the base of 1/2, and then we have 4 minus 2 squared. And of course, that last term will sum to 0. What does this simplify to? I'll type this into my calculator. The value I got was 4.25, and clearly this is an underestimate. It's not stated in this problem, but let's say you wanted to get a very accurate estimate of the area that's between the function and the x-axis. You could use something like n is equal to 10 million. Just to get an idea of what that would look like and why it's a good estimate. So here's the function from 0 to 2. This means the base of each rectangle is going to be 2 minus 0 over 10 million. And I don't really know what that number is, but I know it is small. In fact, if you try to draw this in here, each rectangle is basically going to look like a straight line. So you're dividing this interval into 10 million equal parts. And then when you try to construct a rectangle, let's say using r sub n, it's going to look something maybe kind of like this. Obviously, I'm not drawing in 10 million rectangles, but there's going to be a lot of them. So the second that n gets very large, you're getting a more accurate idea of the exact area under the curve. And you can continue this process forever. You could do 20 million, 20 billion. Each time you're getting closer and closer and closer to the exact answer. The point of bringing this up is we eventually want to be able to figure out, well, what is the exact answer? And to do so, we're going to have to use the idea of a limit. You can always improve on this the larger n is equal to. So if you want the exact value, you can find this expression and then take the limit as n approaches infinity. Let's talk about this on the next slide. So how do we get a formula to figure out the exact value of the definite integral? So if we want to compute this thing, and let's say this graph here is some random function, we'll call it y is equal to f of x. Again, the thing that we're looking for is, if you start at some value a and end at some value b, we want the exact area that is under this equation from here to here and above the x-axis, so this stuff. The approach is, well, you can use any of the L sub n, R sub n, or M sub n methods. You take the interval from a to b, and you divide it into n equal parts, and this will give you a base for all of your rectangles. And the more that you put in here, the more accurate your answer is going to be. You then let n go to infinity, and that'll put basically infinitely many rectangles under this function. So the procedure is, okay, find this, or maybe find this, or find this, and then let n go to infinity. You can think of this definition as the limit as n goes to infinity of L sub n, or the limit as n goes to infinity of R sub n, or the limit as n goes to infinity of M sub n. Any of these will work. We'll typically use this one in the middle, and let's make this a more rigorous definition, and we'll talk about that on the next slide. So here is the formal definition for the definite integral. It's the limit as n approaches infinity of the sum of I going from 1 to n of the function f of x sub I times delta x. It's a very complicated definition, but I don't want to lose meaning of what it's saying to do. The part that appears here is find the area of a rectangle. The height is f of x sub I, and the base is delta x. So this is the area of some rectangle. You then add the areas up. You then repeat this process by letting n go into infinity, because the more rectangles you use, the more accurate your answer is. So I'm going to actually try to derive this thing by using this picture down here, where again, this is the function y is equal to f of x. So let's call our starting point here a, and we'll call the ending point b over here. So step one is you choose n rectangles. Now you need to find the base length of each rectangle. So we take the interval, we find its length, and then divide by the number of rectangles that we're using. The next thing that we would do is actually draw those rectangles in here, which means I have to divide this interval into n equal pieces. The best way I could express this is by saying, like, all right, maybe here's the first rectangle, the second one, and the third one. And this, it continues for a while. Then you got some random one here in the middle until you end up at the one at the very end. It'll be helpful to label these. So if this is our starting point A, maybe I'll call this first one x sub 1. And then maybe I'll call this next one here, I'll call it x sub 2. And then maybe the one after that is x sub 3. In the middle, we're going to end up at some rectangle that's between 0 and n. So I'll call it maybe x sub I minus 1 and then x sub I. And eventually we get to x sub n minus 1, and I can call b x sub n, where the nth rectangle is located. There should be some formula that tells you how to get to the, let's say, ith rectangle, this spot right here. Well, let's say you want to get to x sub 1. How many times would you have to add the base of the rectangle from A to get to here? If you want to end up at x sub 1 and you're starting at A, you would simply add the base of the rectangle once, because this length here is delta x. Let's say you're starting here and you want to get to x sub 2. How many times would you have to add the base of the rectangle to get there? Well, that's going to be twice. If you want to get to x sub 3, you'd have to count 3 times, and so on, and so on, and so on. If you wanted to get to this spot here, you'd have to count I number of times. You're always counting by the number that appears here. And this gives us a formula in general. You can say that the location of x sub I is equal to our starting point plus I times delta x. All right, I'm going to draw in the actual rectangles. So let's see, when we draw in the rectangles, if I'm using right endpoints, I get one here, I get one here, I get one here, and so on. There'll be a bunch here in the middle. There's going to be one at the ith location, and then there's going to be this last one here. I want a formula for the area of all of these. I then want to add them all up, and then I want to put more and more rectangles in there to get a better and better estimate. So what is the formula for any rectangle between here and here? You can use this as a guide with right endpoints. The length of the base is delta x, and the height is the function evaluated at the right endpoint, which is x sub I. So that's exactly what this part of the definition says. F of x sub I is the height of the rectangle, and delta x is the base. This is the area of each rectangle. So we found the area, a formula for the area here, 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 and here, all the way through. You have to add all of those areas up if you want an approximation, so we put a sum in front of it. And then at the last step, we would take the limit of this thing as n goes to infinity. So this is the formula that we're going to use, and essentially what we're doing is we're finding the areas of rectangles, and then we're repeating this process forever to get a better and better estimate. So at the start of this lesson, we estimated this definite integral. Now we're going to find the exact value of it using the limit definition of the definite integral. We'll also refer to these formulas here. You do not have to memorize these formulas, but you do need to know how to set up the limit definition for this definite integral. So let's start there. So we're trying to compute the definite integral from 0 to 2 of x squared dx. So this is the limit as n approaches infinity of the sum of I going from 1 to n of f of x sub I times delta x. So we need to know, well, what is delta x? It's the length of the interval divided by the number of rectangles that we're using. It's 2 over n. So excellent, I know this. You also need to know what is x sub I. We can find x sub I by starting at 0 and counting by delta x. So our formula was x sub I is equal to our starting point, which is 0 in this example, and you count I times by the length of the base of each rectangle, which is this. I'm going to simplify this to 2I over n. Now our function f of x is equal to x squared, and we want f of x sub I. So I'm going to put x sub I, this thing, here and here, and that means f of x sub I is equal to 2I over n squared. That's 4I squared over n squared. I'm going to take all this information and put it into our formula. Let's see what we get. This is the limit as n goes to infinity of the sum of I going from 1 to n of f of x sub I, that's 4I squared over n squared, times delta x, which is 2 over n. Our job is to now somehow compute this thing. That means simplify this, figure out its sum, and then take the limit as n goes to infinity. I see I can multiply the n's together to get n cubed, and 2 times 4 is 8. So I think I'm going to write this as the limit as n goes to infinity of the sum of I going from 1 to n of 8I squared over n cubed. At the start of this lesson, we talked about a couple of properties that the sum, the sigma notation, has. Anything inside the sum that's not changing, that's constant, can be factored out. I squared is changing because I goes from 1 to n, but 8 never changes, nor does n cubed. I'm going to factor that out and put it here. So this is a property that sums have. All right, so plug stuff into the definition, simplify it a little bit, factor out a constant, and we have this thing here, the sum of I going from 1 to n of I squared. If you look at this thing, and this will always happen in the process, this can be now substituted with this. We've reduced things down to a formula that we have. So instead of writing this, I'm going to swap it out and replace it with this. This means we have the limit as n goes to infinity of, so we have 8 over n cubed, but that's multiplied by n times n plus 1 times 2n plus 1, all divided by 6. This is important. In this process, this should always happen if we're able to compute it. We can end up with a sum whose formula we know. Therefore, we can just get rid of the sum altogether. The goal now is just to figure out, well, what's this limit equal to? This looks pretty complicated, but it turns out there's a nice way to express this so you can easily determine the limit. I'm going to interchange the location of 6 and n cubed. So I'll put the 6 here and the n cubed here. And we have 3 products in the numerator. I'm going to take one of these n's and divide it into n, take the second one and divide it into n plus 1, and take the last and divide it into 2n plus 1. The expression becomes this. It's the limit as n approaches infinity of 8 over 6 times n over n times n plus 1 over n times 2n plus 1 over n. This is equivalent to this. If you multiply the denominator, you get 6 times n times n times n. That's 6n cubed. And the top is 8 times n plus 1 times 2n plus 1, which is this. But I claim that as n goes to infinity, we can easily figure out what happens to these parts of the product. Well, first of all, we can just even cancel those n's. I mean, those are gone. This is the limit as n approaches infinity of 8 over 6. Then we have n plus 1 over n. And then we have 2n plus 1 over n. What is the limit of this expression as n goes to infinity? What is the limit of this expression as n goes to infinity? You can look at the coefficients in front of the n terms. In the top, we have 1 and 1 in the denominator. That means the limit of this whole thing is equal to 1. In the second term, we have coefficients of 2 and 1, and therefore the limit of this is 2. It makes it very easy to compute this entire limit. 8 over 6 is fixed. This thing goes to 1. This goes to 2. And therefore, our answer is 8 over 6 times 1 times 2. And we can simplify that a little bit more. 2 goes into 6 3 times. 8/3. That's the exact answer for this definite integral. So the area that we were estimating at the beginning of the lesson is exactly equal to this. This is a very complicated formula. And it turns out that the second your equations have slight bends or curves in them, we're going to need something this complicated to get our answer. Let's try this one more time in example 7 with a slightly more complicated function. Here we have 2x squared minus 3x plus 1. And we're looking on the interval from 0 to 1. We're going to figure this out exactly by using these formulas here. So we want the definite integral from 0 to 1 of the function 2x squared minus 3x plus 1. Well, we need to know delta x. Delta x is equal to the length of the interval divided by the number of rectangles that we're using. And so this is just 1 over n. We need to know x sub I. That's equal to our starting point, which is the lower bound of 0, plus I times delta x, which is 1 over n. And this whole thing just equals I over n. Our function f of x inside the integral is 2x squared minus 3x plus 1. And here we have to figure out, well, what's f of x sub I? If we plug in I over n into all the x's, we get 2 times I over n squared minus 3 times I over n, and then plus 1. Therefore, this is equal to the limit as n approaches infinity of the sum of I going from 1 to n of f of x sub I times delta x. The process in this example will be the same as the last. It's just a slightly more complicated function. This is the limit as n goes to infinity of the sum of I going from 1 to n. Okay, f of x sub I, it's equal to this thing. I'm going to square this out and write it as I squared over n squared times 2. So I'll put 2I squared over n squared minus 3I over n plus 1. And this is all multiplied by delta x, which is 1 over n. And therefore, we want the limit as n approaches infinity of the sum of I going from 1 to n of, if I multiply in 1 over n, I get 2I squared over n cubed minus 3I over n plus 1 over n. This is different than the last example because now we have a difference and a sum, whereas last time we just had a single term. The other important property of sums is that if you have a difference or a sum, you can split this up into 3 separate sums. It will look like this. This is the limit as n approaches infinity of the sum of the first thing, which is 2i squared over n cubed, minus the sum of the second thing, which is 3i over n, plus the sum of the last thing, which is 1 over n. Now, in each part of these sums, anything that does not depend on I can be factored out. So this is the limit as n approaches infinity of, okay, in that first sum, we can factor out 2 and n cubed. And then left over, we have the sum of I going from 1 to n of just I squared. Then we have minus, we can factor out 3 over n, and we're left with the sum of I going from 1 to n of, okay, that would just be I. And then plus, we can factor out the 1 over n. And we have the sum going from 1 to n of just the number 1. Here, if you multiply this back in, you would have 1 over n, because 1 over n times 1 is 1 over n. Here, I have this formula that I can refer to, this formula I can refer to, and this one I can refer to as well. I'm going to replace these 3 things with their corresponding formulas, and I'll do that on the next slide. And actually, I see I missed something. When this gets multiplied here, there's an n times n in the denominator. This should be squared, that should be squared, and this should be squared. I'm going to go ahead and add those in. So this should have been squared here, here, and here. So when I multiply this into these 3 terms, the exponent should increase by 1 on all of them. So it should be this. So for the first one, we had 2 over n cubed, and that first sum is n times n plus 1 times 2n plus 1 all over 6. The next thing we had, let me just write that a little bit better. That's 2n plus 1. Then we had minus 3 over, it was supposed to be n squared, and that's times n times n plus 1 over 2. And then lastly, we had 1 over n times its corresponding sum, which equals n. All right, a lot simplifies here. I'm going to use the trick that we did in the last example. What I'm going to do is interchange these 2 values and these 2 values, and I'm going to break it up into 3 separate fractions because I can divide n into those 3 terms. I can divide n squared into those 2. So this whole thing is 2 over 6 times n over n times n plus 1 over n times 2n plus 1 over n minus 3 halves n over n times n plus 1 over n, and then plus, well, you could just write this as n over n. Now, any n over n just simply cancels, and those are all just going to be equal to 1, which I don't even need to write for these 2 terms here. So let's rewrite this limit. This is the limit as n approaches infinity of, okay, well, 2 over 6, that's a third. I'll just put 1/3 times n plus 1 over n times 2n plus 1 over n minus 3 halves times n plus 1 over n, and then plus 1. I'll note that as n goes to infinity, this goes to 1, this goes to 2, and this goes to 1. And that's because we're looking at the ratio of the coefficients of the highest powered n terms. You can actually just write the answer down at this point. This is going to be 1/3 times 1 times 2 minus 3 halves times 1 plus 1. So that's 2/3 minus 3 halves plus 1. And when simplified, this gives us a value of 1 over 6, and that's the value of the definite integral.